bisector does? Well, it bisects an angle, hence the name angle bisector. Convenient. So if you bisect an angle, you create two congruent angles. We know that from all the progression stuff, all the proof stuff that we've done in the past. So what I want you guys to do is draw an angle a little bit bigger so that way we can label some stuff. We know that that has to happen. Choking in water.
How long
Apparently.
have you been drinking water?
Ooh.
You still don't have it down?
What's that?
How long have you been drinking water?
I don't know. For apparently not long enough. So part of that I think part of that apple's stuck too. So.
Oh yeah, you said when you bite an apple and you think
Oh.
tired of it.
Yeah, that apple wasn't all that great. Excuse me. All right. So we know that angle bisector does. Obviously, it bisects the angle. Two congruent angles are formed.
This is really annoying.
Whenever you guys are ready, it'd be great. Okay. Now, just like we did yesterday, if you place a point on that bisector, some other things occur. If you put a spot or place a dot on the bisector at any point, a couple things happen. First thing that happens is that you wind up being equidistant to both sides of the angle. Now, what I mean by equidistant is that that's going to be congruent, but the way that you measure distances, or basically I'm going to say the shortest distance between 2 points, the way that we measure those things out is via a right angle. We call it a perpendicular distance. So when you measure something out, when I'm measuring from here to the wall, I'm not going to measure it to the corner. I'm going to measure it to where it's what we call square. So when you're talking about this equidistant stuff, it means it's going to create right angles here and here. We measure a square distance. A lot of times people will call it that. Check to see if something is square. You do that in building. You do that with framing. You build a wall, hang cabinets. At some point in your lives, you might actually, do a house project. I know it's hard to believe that someday you might actually want to, finish a basement, put in a patio, build a deck. Any of you guys ever notice a door that gets stuck sometimes when you're opening and closing? You gotta shake it a little bit, or you tilt it just a little bit and it opens up freer? It's because it's off square. Because it's not, what that means is that the corners don't create right angles. One of the things that you will actually, honestly and truly use from a high school geometry class is this little trick. If something is going to be square, you don't have to write this out here. If something is going to be measured out to be square in a corner, you have two sides. If I create the other side here, what do I make? More specifically, I should have a right triangle. So what people do, and you do this really with anything, is that you measure out easy distances to see if something stays square. For example, if I measure out 3 feet here and 4 feet there, if those two are going to create a right angle, the Pythagorean theorem has to hold true. So what's 3 squared? What's 4 squared?
16.
What's 9 and 16?
25.
What's the square root of 25?
5.
5. So if I measure out 3 feet in one direction, 4 feet in the other, from the endpoints that I'm measuring, that should always be 5 feet. It works the same as if you double all of that. If I double 3, what do I get? If I double 4, what do you get? 8. What's 6 squared? What's 8 squared? 36 and 64 is 100. What's the square root of 100? Which happened to be 5 double. It's a very common thing, so that when you're trying to build out, if you ever go and you start to frame out a basement, you build your walls up, but before you ever see those, the guns they hit with a hammer and it shoots a bullet down into the concrete? That's how you put things onto concrete. So what a lot of times, before you do that, you measure out distances, 3 feet, 6 feet, just to make sure your walls are waverly, like, you know, going inward or outward on whatnot. Because if that happens, when you put up drywall, everything gets all nasty. It gets all out of whack. That's when you see wavies in your walls and stuff, and things don't look nice and flush. That's why carpenters use this. That's why people, whenever you build anything, you check to see if it's square. You bring things out so many distances and you measure across. It works. That's how this works. Geometry actually has a purpose, and this is one of the biggest things you guys will ever use. Seriously, and I'm not lying. You'll come across this later in life, big time. So that's why we use this thing called a perpendicular distance to measure stuff out. It's the shortest distance between 2 points, and it always makes a right angle. So bisector stuff is actually really, really easy to work with. If you're on an angle bisector, you are perpendicular and equal distant to the sides. It's that straightforward. And just like we've done in the past, where if you were able to say a definition in one direction, you could say it in reverse. So instead of saying, if you're on an angle bisector, you're perpendicular and equidistant, you could say, if you're equidistant and perpendicular, then you are on the angle bisector. So what we call that biconditional statement. It means it works going both ways. Okay. Excuse me. Stop. So algebraically then, we can do stuff like this. In order for this to be on an angle bisector, the angle has to be bisected. Well, if an angle is bisected, what's created? 2 equal angles. So if one angle is 13x and the other is 11x plus 8, what would you do to solve for x? Set them equal to each other. This is really, really straightforward. Okay. Really straightforward. So we've done this before where it asks you to figure out a value so that way it works up to lie on something, whether it was a perpendicular bisector, an angle bisector. Tomorrow we'll talk about medians.
So it has to be square to the side?
Yeah. Yeah, because if you ever want to measure, if you think about it, if someone ever asks you how tall you are when the doctor measures you, you go up against the wall, you stand up nice and straight and tall, you don't slouch. Because that way you're as tall as you can be. So it's kind of the same idea as you go through. Okay. So algebraically here, this is real quick. You just got 2 variables on both sides. Take on the little guy, move the 11, and you get 2x. And what's x? 4. It only takes a second to double check and make sure you didn't goof. 13 times 4, well, that's easy. Double 13, what do you get? Double that, and you get 52. So 13 times 4 is 52. 11 times 4 plus 8 is also 52, so we know we didn't screw up. Or, please, make sure you have a calculator, ladies and gentlemen. You kind of have to have it. Okay? No, it's all right. I just want to get you sure. Like I said, it's really straightforward. Gee, in order for those two to be, well, in order for it to be on the angle bisector, well, the angle's been bisected. Are they perpendicular to the sides? which means they have to be congruent. So what do you do algebraically? Set them equal to each other. This should take you about 30 seconds. Did you get 9? See, it's already been bisected. Perpendicular, which means this has to work. So it's add 9, subtract 3x. Very, very quick.
I didn't say anything.
I didn't look like you were about to. What do you want?
Will there be like, will there ever be a time where the bisector isn't there and we have to solve it for ourselves? Or,
What do you mean?
like with the bisector on the corner, will there be a time that we have to solve it on our own to find it, or will it be given to us?
Well, you have to be given some information. And I think you're worrying about like what we did yesterday where we had 3 of them. That's what we're getting to next.
Okay.
Okay, it's actually really easy. You have to trust me again. Because yesterday was easy. It's just a matter of, the idea here is being able to keep up on what everything's called. Just like yesterday when we had those 3 perpendicular bisectors intersected, you can also have 3 angle bisectors intersected. That's called an in-center, where they run into each other. So it's not that the math or any of this stuff is going to be really all that difficult to work with. What's going to be difficult is to keep straight the vocabulary. The circumcenter, you'd have to know what that means. An in-center, you got to know what that means in order to make it work. Okay? So the in-center is the point at which all 3 angle bisectors hit. Oh, that was yesterday. Okay. The in-center is where the angle bisectors intersect.
Oh, so I was going to say
Okay. Now what happens with this point, just like yesterday, it was from that point to vertex that was congruent. Today it's going to be the point to side. Actually, I should say this. Point is perpendicular to the side, and they are all congruent. Let me just draw this up for you. Those 3 segments are the same. The inside segments are all congruent and perpendicular to the sides. That's it. Okay, that's it. Yes, ma'am.
So this one is the angles and yesterday was the sides?
Yeah, yesterday was perpendicular bisectors. Today are angle bisectors. Tomorrow will be medians.
Okay.
We'll talk about altitudes, but there's really no math involved with altitudes. It's just a name that we'll worry about. So in-centers are the point to side.
And all congruent.
Okay? It's the segments inside. Point to side. Which means, just like yesterday, you've got a whole bunch of little right triangles. Which means you're probably going to have to use, oh, I don't know, Pythagorean theorem once or twice. That's about it. I know. It's crazy how they anticipate the fact that you guys know the Pythagorean theorem, but yet they haven't defined the Pythagorean theorem for you yet. It's convenient. It's like asking you guys to find the area underneath the curve. You don't know how to do that, but you could. Let me show you a problem. I didn't have this one drawn out for you, but this is actually really easy to draw up. Angle bisectors are quick. Yes, ma'am?
Nice question.
Angle angle bisectors are really easy to draw and work with. So here it tells you, just like we did yesterday, they're going to use this vocabulary. V is an in-center. If it gives you that kind of information, like I've been trying to hint at, you have to know what to label in your diagram to show what's going to work. So we have this large triangle, was it QRP, and then V is the insect, where all the angle bisectors run into each other. When you have that, that means everything from the point to the sides are congruent and perpendicular. Well, they gave you all the perpendiculars. You just have to do this. So if I need to find VS, isn't that the same as finding VT or finding VU? So you look at what information you know, just like you did yesterday. Looks a whole lot exactly like what you did yesterday. How are you going to solve for x? Was it? Yeah, but I didn't hear how you were going to write it out.
15 squared plus 3 squared, well, x squared.
Yeah, I didn't hear what you had said for that part. Yeah, and that's all it is, guys. So if I move the, oops, I didn't want to move. This one down here. If we're working just with that, it's just x squared, 15 squared, 17 squared. And it's exactly like, well, almost exactly like what you worked with yesterday. Just push buttons on the calculator. Yes, ma'am.
How are you knowing which one you're gonna put like next to x and which one you're gonna like
The order?
yeah, like the order?
Okay.
Yeah.
When you use Pythagorean theorem, it's horribly bad drawing. When you're using Pythagorean theorem, this is always the c value because the hypotenuse
Oh,
is always across from the right. The other two are called legs, and they're totally interchangeable. One is A, one is B, and it doesn't matter which one's which. Okay? So if you know that across from the right angle is 17, that's always the hypotenuse. And then you just go from there. Does that make sense?
Yeah, that makes
Okay.
sense.
Yes, ma'am. Flip it. Yeah, 17 squared minus 15 squared. Yeah, I was just making, yeah, that's what we're doing. So you fill that out, you get x squared is what you were just saying. And you're right, simple algebra, press a couple of buttons and you get 8. You get a couple of buttons again, it'll give you 8. Okay. Now, that's what we're at. Actually, that's what we call a Pythagorean triple. A Pythagorean triple are 3 numbers that are always work with the Pythagorean theorem. Like we did a second ago, that 3, 4, and 5, that's a triple. It's a family of triples. If I double it, I had 6, 8, and 10. If I triple it, I had 9, 12, 15, and so on. If I have that as my basic values, whatever I do by some sort of scalar, by multiplying it by some value, it will always work. Same thing with this one, 8, 15, 17. It's another one of the family of triples. We spend about a day day and a half or so sometimes talking about the triples in second semester. They're not so much something that you're gonna have to memorize themselves through. They're family values that if you recognize it, the math is just faster. You'll have a calculator to do all the work, so you don't have to worry about doing that more often than not. But it just makes it quicker if you know the triples, because you just pick up on the patterns. You know, if I say I see a 6 and an 8 for 2 legs, I know the other one has to be 10 because it's a triple. It's one of those things. It used to be more heavily emphasized than it is nowadays. You do see it often in not sorry. What are those things called? Like ACTs, SATs, things like that. We use Pythagorean theorem just about every other day, second semester.
So then with the VS, would that?
Yeah, it would also have been 3.
Oh,
Oh, I'm sorry, 8, yeah.
Yeah.
Because if this was 8, that means this is 8, which means this is 8.
Okay.
That's all it is. Now, don't draw this. Let's just see if you can figure this out in your head. No, read it. D is the in center. What's DE?
5. Would it be 5?
D is the in center. What is it? Where is it congruent on the in center?
3. Oh, I was going with E.
The in center is the point to side. So what is it? 3. Sometimes it's that fast. Okay. What would GC be? It's got to be 4. Remember we just talked a second ago about 3, 4, 5? Pythagorean theorem. The Pythagorean theorem says 3 squared plus 4 squared is 5 squared. Like I said, there's really not much to these things, believe it or not. One of the things that does happen is this. Now, I don't want you to completely draw this out, and I want to just kind of redraw just the right triangle that we're going to work with here. If N is the in center, is everybody okay by saying that all the blue segments in there are the same? Because that's all from the point to side, that's all the perpendicular parts. So if I look at it, we have this triangle to work with a 37, 35, and a 2x. Are we okay with that?
Yeah.
All I did was just move it around so that we do all those blue verticals were all the same. I still can use Pythagorean theorem here. Here's what you have to be careful with. It's still this squared. When you square this side, the side length is 2x, which means it's quantity 2x squared. That's what you guys are going to screw up. If the x value, if the x has a coefficient, that part also needs to be squared. No, the x is the variable, the coefficient is the number in front of it. So if there's a coefficient that's not 1, because if you don't see anything, it's always a 1. If it's anything else, you have to make sure you square that number too, because it's always that side value is 2x. Well, the 2x quantity squared becomes, well, what's 2 squared? And what's x squared? What's x squared? x squared. So
You don't know.
2x quantity squared is just 2x times 2x,
But you don't know next.
which is 4x squared. This is the type of algebra then that we're going to wind up seeing. It's not that it's any difficult. Really, all it does is add one step to what we've been working on. You still subtract it over like you did before. But I want to show you guys how you use your calculator to solve these types of problems. All I did there was just move that 35 squared over, just like we did before. We were adding it, so we subtracted the other side. I would type in my calculator, 37 squared minus 35 squared, and then hit enter. Which means I have 4x squared. Can't. I can't square root that because what's in front of the x? 4. So you have to divide by 4 first. Okay? In order to make this work, you have to divide by 4.
Why do they have to make it so confusing?
It's not confusing. You're just solving an equation. You're working backwards from solving an equation. You're using the order of operations in reverse.
I forgot that.
Don't forget that. That's why I'm showing you this. And I believe that's 36.
2 years.
Do I have to press that in the calculator, or do we know what the square root of 36 is? It is?
Wait,
Okay. Quite honestly, that's about as goofy as some of this stuff gets, because you're going to forget that you have to multiply. When you square junk, it's junk squared, so it's junk times junk. Or you'll forget that you have to divide first before you take the square root. Don't do that. That's bad. Okay? Yes, ma'am.
Why do we put 4x on the other side of the, like, why did we do that thing where it's 4x equals, yeah,
We started here with our triangle.
yeah.
All I did was I moved this number over first. So I had 4x equals 37 squared minus 35 squared. And then I had this equaled 144. So it's 4x squared is 144. I have to divide by 4 before I take the square root. You're working backwards from order of ops. That's it. Okay? Try another one like that. So I know this is where things get goofy.
why did you start it?
Same deal again. If I'm going to work with something that has to be an in-center, and I don't want you to try and draw this whole thing out. I just want you to figure out, well, what's the triangle that you have to create? Well, it's a two-step algebra problem.
But it's like that, especially for somebody that's not a person.
Well, we can do it. It's just 2 steps. All right? And you got a calculator. So in order for it to be the in-center, you know that all those segments that are in blue have to be the same. So just draw that part. Don't overwhelm yourself with the whole picture, because it gets to be kind of muddy. So you've got a right triangle with a 14x, a 24, and a 25. And you do the exact same thing we just did. You use Pythagorean theorem just like before, but when you have a coefficient, you got to make sure you put it in parentheses. Okay? And you start filling in blanks. 14 squared is 196. Is it wrong to multiply out 25 squared and 24 squared? No. Is it just as easy to just leave it like that and move it? You're just pressing buttons at that point.
Hello, sleepyhead. How are you?
I don't ask for much. Staying awake is usually a good thing. Tell her he's not sleeping? Oh. So 25 squared minus 24 squared is 49. Now guys, please pay attention to what you do now. I can't take the square root here because there's something in front of it. You have to do this. Now, your calculators will do this for you, okay? Your calculators will do this. If you type in your calculator, square root of a fraction, oops. Your calculators will do a square root of a fraction just by pressing the square root button and then the fraction bar. Then all you have to do is type in the numerator and denominator and press enter. It'll do the work for you. It's the whole idea of buying one of those calculators. There's your answer. It's 1/2. Yeah, but yours will give you a decimal. You're not going to want decimals second semester because I am being simplified radical form, which winds up being fractions. These calculators do all the fraction work and all the radical work. They'll leave things in terms of pi that are on the circles, but keep all the answers. They won't give you decimals. They'll give you exact answers. That's why I've been saying since August, you need a calculator. No. Okay. So like I said, that's about as goofy, guys. That's about as goofy as any of this stuff gets, just by working with those two-step equations. What I have to do, I want you to do all of these except for 17. Okay.
So do they like
you're supposed to like take these classes to these classes. But if you did, I think if you did, I think if you did like recovery, or if you make up the class when you're in the
yeah, I did a lot of freaking credit recovery.
I failed second semester in humanity.
Oh, come on!
Second, no. I failed. Yeah, I failed second semester in biology last year. And those are the only 2 classes.
So do all of these except for 17, please. 17 is, there's not wrong with 17.
You're gonna have to take it
To interpret 17 is a little goofy, so there's no reason. I would suggest starting on the back because that's this. Guys, I would suggest starting on the back and working your way to the front because the ones on the back look just like the ones we just did in class.